Good morning everyone. At the outset I would like to thank the Academy for providing me an opportunity to deliver this talk. Today I will be presenting on electronic structure engineering for the development of high performance thermoelectric materials. Thermoelectric materials are the materials which have the ability to convert temperature difference into electric potential. There are two kinds of thermoelectric devices. One is thermoelectric generator and the other one is thermoelectric cooler or Peltier cooler. So this is a schematic representation of a thermoelectric module wherein the P and N type legs are connected electrically in series but thermally in parallel. In case of thermoelectric generators, the temperature difference applied across the P and N type materials generates electric voltage because of the diffusive flow of charge carriers, while in the case of thermoelectric coolers, voltage applied brings about temperature difference. So world's demand for energy is primarily met by combustion of fossil fuels. This has an adverse effect in the form of global warming, and also about 60 to 70% of energy utilized is wasted in the form of heat. Now if this heat could be scavenged, then that would be great. So this is where the thermoelectric materials come into picture. So although all the materials have got non-zero thermoelectric effect, but in most of the materials it is too small to be useful. And despite low efficiency of thermoelectric materials, they are used in a variety of applications basically because of their reliability. Thermoelectric devices have the advantage of being they are kind of stable, they are solid state devices, they do not have any moving part, okay, and because of this they can be used in harsh environments for extended periods of time without human intervention because they are maintenance free. So now why is this work challenging? The effectiveness of a thermoelectric material is given by the dimensionless figure of merit and the efficiency is given by this equation. Here alpha is the Seebeck coefficient, sigma is the electrical conductivity and kappa is the thermal conductivity. So this factor is called as the power factor. So in order to have high figure of merit, we need to have high power factor and low thermal conductivity. So now if you see here, Seebeck coefficient is inversely proportional to carrier concentration, whereas electrical conductivity is directly proportional to the carrier concentration. So hence if we increase the carrier concentration, the Seebeck coefficient decreases and the electrical conductivity increases. Now since electrical conductivity is linked to thermal conductivity, that is the electronic component of thermal conductivity, the thermal part gets tied up to the electronic part. I said thermal conductivity has to be lower, and there are two sources of thermal conductivity. One is the electronic thermal conductivity, which is because of the electrons and holes carrying the heat, and the other one is lattice thermal conductivity, which is because of phonons traveling via lattice. So how should a material be? The material should be high in electrical conductivity, that is like a metal, and it should induce high voltage in response to a temperature difference like a semiconductor, and it should be a poor heat conductor like glass. So now how do we design a high performance thermoelectric material? Okay, lead telluride is one of the most well known thermoelectric material, but because of the toxicity of lead, its usage is not advisable. Tin telluride on the other hand is its rock salt analog and it has similar electronic structure. But tin telluride is a very poor thermoelectric material, okay, because of its intrinsic vacancies which increase the carrier concentration, and also it has high thermal conductivity. And also if we look at the electronic structure, we see that tin telluride has smaller band gap in comparison to that of lead telluride, and the energy offset is higher, which means these bands do not participate in the transport. So what are the strategies to improve the power factor? As I said, carrier concentration is one of the important parameter. It could be tuned either by self compensation or by donor doping, and power factor can also be improved by band structure engineering. So if we see here, we see that when the temperature increases, the band gap increases, but yet it is not sufficient enough to prevent the bipolar diffusion, which is detrimental to ZT. So therefore, if we can add a dopant such that the band gap increases and the valence band offset decreases, then it would be promising. The Seebeck coefficient of a material is directly proportional to density of state effective mass, which is given by this equation. Here NV is the number of degenerate valleys and MB star is band effective mass. So in case of tin telluride, we have valence band, that is light hole valence band at L point with NV of 4, and we have heavy hole valence band at sigma point with NV of 12. So when we converge these two, then we will have increased NV. So increase in NV can be visualized as increasing number of lanes on the road, so that it will facilitate smooth traffic. So increased NV here means there is more number of conduction pathways for the charge carriers to take part in the transport. Also another way of improving the power factor is by introducing resonance level. Resonance level arises because of the coupling of electrons of the dilute impurity with that of the conduction or valence band electrons. This increases the density of state near the resonant energy. If the Fermi level can be brought close to this, then we will have increased MB star and in turn Seebeck coefficient. And here as we tune the electronic structure, what the dopant what we have added will also reduce the lattice thermal conductivity because of scattering of phonons of short mean free path. Lattice thermal conductivity is the only parameter which is independent of carrier concentration, and it can be decreased either by atomic scale, nanoscale structuring, mesoscale structuring, or employing all of these together in all scale hierarchical architecture. Now what happens is, when we introduce a nanoparticle within a bulk material, there may be generation of additional energy barriers, either because of the crystallographic mismatch or the band misalignment, and because of this there will be scattering of the charge carriers and it decreases the mobility of the charge, and hence we need to decouple the electron and phonon transport, and it can be done either by strained endotaxial nanostructuring, matrix precipitate band alignment, or by compositionally alloyed nanostructures. So now let us see how electronic structure engineering can be used to improve the performance of tin telluride. Magnesium and calcium were known to increase the band gap of the tin telluride and also cause valence band convergence, and indium was the only known resonant dopant till 2019. So when we co-dope this, we see that the dopants play different but complementary role. Indium increases the performance at lower temperature, while the other two dopants increase the performance at high temperature. In the case of magnesium indium co-doping, we achieved a ZT, that is the figure of merit, of 1.5 at 840 Kelvin. In case of calcium and indium co-doping, since calcium had higher solubility, we maintained 2:1 ratio and we achieved a ZT of 1.6 at 840 Kelvin, and this material exhibits the highest power factor achieved by far in SNT based material. So now the previous technique wherein you co-dope two different dopants, though they increase the performance at higher temperature, the performance at lower temperature was mediocre. So there was necessity to find some other approach to improve the performance at low temperature. So bismuth, which was basically used to tune the carrier concentration of tin telluride, we studied its electronic structure and we saw that the p orbitals of bismuth hybridized with the p orbitals of the host, giving rise to what you call resonance level. So for the first time we tried co-doping a p-type and an n-type resonant dopant, and we see that while we increase the concentration of bismuth, the band gap increases and the band offset decreases. So in this case we achieved a ZT of 0.25 at 300 Kelvin, and at 840 Kelvin it was 1.32. So I said indium is a very good resonant dopant, but the problem with indium was when you increase the concentration of indium, the electrical conductivity drastically decreases, and hence we were trying to find some other kind of resonant dopants. So the electronic structure of zinc doped SNT showed promising features. Here we see that the zinc s orbitals hybridized with the tellurium p orbitals, giving rise to resonance level, and because of the increased density of state and increased effective mass, we see that the Seebeck coefficient drastically increases at room temperature, and this material exhibited a ZT of 1.28 at 300 Kelvin and 1.49 at 840 Kelvin. So in order to further improve its figure of merit, we co-doped it with the bismuth, and in this case the bismuth p orbitals, zinc s orbitals hybridized with the host p orbitals, giving rise to resonance level which almost mirror each other. This unique electronic structure led to a record high room temperature ZT of 0.3 in lead free SNT based material and a peak ZT of 1.6. So we can see that zinc doping helps a lot in improving the thermoelectric properties of tin telluride, but it has a disadvantage that the lattice thermal conductivity exhibited is high. So now when we alloy lead with SNT, we see that the thermal conductivity drastically decreases, but the problem here is that the band gap also closes, which will lead to bipolar diffusion. So when we dope zinc into it, we see that the band gap increases, there is introduction of resonance level, and in addition to this there is phenomenon of hyperconvergence, that is the heavy hole valence band increases in energy compared to that of light hole valence band, and this increases the Seebeck at room temperature, leading to a ZT of 0.35 and a peak ZT of 1.66, and this material exhibited a average ZT between 300 and 840 of 0.9, which is actually a record high value. And when instead of zinc, when we doped bismuth, we predicted a ZT of 1.58 at 800 Kelvin. So in order to make the material lead free, that is non-toxic, we alloyed germanium, and even in this case we see that the band gap decreases, and hence we dope zinc, which again here led to increase in the band gap, introduction of resonance level, and in this case we see that the bands, that is the light hole and heavy hole valence band, are perfectly converged. Zinc was also co-doped with other elements, and when the ratio was maintained similar for all the three cases, we saw that the lead free silver zinc combination showed maximum ZT of 1.54. So as I said in the beginning, for a thermoelectric material we need both P and N type legs. So when we studied the electronic structure of tungsten doped SNT, we saw that tungsten increases the band gap, it causes convergence of the valence band. In addition, it introduces multiple electronic valleys near the Fermi level, and the unique feature was hyperconvergence of conduction band. This was reported for the very first time in the case of tin telluride, and this feature was not seen in molybdenum or vanadium doped cases, and also the tungsten d orbitals increase the density of state near the Fermi level, and hence we predicted a ZT of 1.61 in this case, and since it showed promising features for both development of N and P type material, so more studies need to be conducted on this material. So I would like to take this opportunity to thank Professor K.S. Narayan sir for nominating me for the associateship. I am also immensely grateful to Professor Krishnabhat sir, who is my collaborator and who has been an immense support throughout my research activities. I thank all the co-authors of my papers. I acknowledge the funding from DST under Inspire Faculty Fellow Scheme, Science and Engineering Research Board under SRS and EMR scheme, and CSIR under EMR scheme. Thank you one and all.
Thank you, Sandhya. A few questions.
The temperature dependence of the band gap,
Yes, sir.
Is it because of the impurities, or for pure substance also?
For pure substances, sir. For pure substance itself, we see that when you increase the temperature, the band gap will open up, but it is not sufficient at high temperature to prevent bipolar diffusions. Because in case of tin telluride, if we see, for about 800 Kelvin, in order to stop the bipolar diffusion, we need a band gap of around 0.4. So, in case of SNT at room temperature, the band gap is 0.18. So, if we consider the temperature effect, that is the band gap opens something around 4 into 10 power minus 4 EV per Kelvin. So, it will be around 0.38. So, still it is not sufficient, it does not reach 0.4, so there will be bipolar diffusion.
So, you have done the calculation, finite temperature calculation?
No sir, that is a well known thing, like the amount of band gap required for a particular temperature, that is already established. What we do is we just check the conductivity values, like what happens is Seebeck and as well as thermal conductivity values. If at all there is bipolar diffusion, there will be an upturn, or in case of Seebeck there will be a downturn. So, based on that we will know whether there is bipolar diffusion occurring or not.
Okay, so you use the Fermi-Dirac distribution for the calculation?
We don't actually calculate what is the amount of bipolar diffusion, we just check the Seebeck coefficient, if it is increasing or decreasing.
Yeah. So when the thermal conductivity decreases when you introduce lead, is that mainly the phonon thermal conductivity going down, or is it also the electronic contribution which goes down?
It's actually the phonon ones, like the maximum thing is phonon because of the weight difference.
Right. So the electronic thermal conductivity is not changing very much. You're saying it's the phonon which is.
Yeah. That's why we add actually zinc. So because it also distorts the electronic structure. So to compensate for that, we add zinc so that the band gap.
I see. Okay. Yeah. Thank you.
Excellent science.
Thank you, sir.
How do you prepare the material, particularly the one with the tungsten? There are high melting materials.
It's seal tube reactions. Like we take the starting materials. We add it into a quartz tube and then heat it to a very high temperature and a vacuum.
By what? Induction melting, arc melting, or what is it?
No sir, for some of the things it's normal melting, like in the oven we reach up to 1200 Kelvin or so, and also in some cases like SHS and all, we directly use a flame torch to heat the samples.
No, tungsten being high melting?
Tungsten we haven't synthesized it yet sir, we have just calculated the electronic structure yet to synthesize.
Okay, thank you.
One lift. Yes, there we are.
I was just wondering, the substitution by bismuth seems to have distorted the lattice. So if you were to take antimony, it might be less of a distortion, and yet you might have similar effect. Is that possible?
Pardon sir?
You had a doping with bismuth.
Yes sir.
If that seems to distort the lattice to some extent.
Yes sir.
Now, if you use instead of bismuth antimony, probably it may not change, because the tin and antimony are not really so far apart in terms of size. So I was just wondering, you have tried
antimony, it's already tried sir. They have, like basically they use antimony to change the carrier concentration, and then they add some other dopant to have impact on the electronic structure.
Okay. Thank you.
Thank you. And if there are no more questions, we thank Sandhya Shenoy for the wonderful talks. Thank you very much.